Welcome back to The Explainer. Today, we're diving straight into a high-stakes biological detective story. We are going to be looking at the incredibly complex interactions between our structural barriers, our microbial residents, and how they ultimately influence the very beginnings of human life. Let's kick things off with a number that is just staggering. 15 million. That's how many babies are born prematurely every single year around the globe. This isn't just some rare biological anomaly. We are looking at a massive global medical crisis. In fact, it's the leading cause of neonatal morbidity and mortality worldwide. When you see a number that huge, it absolutely demands our attention. It forces us to ask, what exactly is going wrong at a fundamental microscopic level to cause this? Just to make sure we're all on the exact same page here, let's define what we're actually talking about. Preterm birth is defined as any live birth that happens before the completion of 37 weeks of pregnancy. And babies born before that threshold, they face a significantly higher risk for severe short-term complications like respiratory distress and sepsis, not to mention long-term neurodevelopmental and cardiovascular issues. It is a literal race against the clock, and the stakes simply could not be higher. So, how are we going to unpack all of this? We've got 5 quick parts on our agenda today: the preterm birth crisis, the mucus gatekeeper, the vaginal microbiome, when the barrier fails, and finally, predicting preterm birth. Section 2, the mucus gatekeeper. I want you to think of the uterus during pregnancy as a highly protected, perfectly sterile fortress. For a pregnancy to succeed, that fortress has got to stay locked down. The main defense for this fortress is the cervical mucus plug, or the CMP. It physically fills up the entire cervical canal, acting as the primary barrier that stops the bacteria naturally living in the vaginal mucosa from ascending into that sterile uterine compartment. But if things get thrown out of whack, a state we call dysbiosis, that plug can become porous or shortened, and it allows ascending bacteria to sneak right past the gates. So the health of this plug is absolutely vital. Now, you might be thinking mucus is just, well, a static blob or a physical wall. No way! The CMP is actually this incredibly complex, viscoelastic, gel-forming network of mucins. It is packed with active biochemical defenses. It keeps a low pH to deter pathogens. It carries a negative charge to literally repel certain invaders. And it's filled with antimicrobial compounds and protective microcolonies that actively block pathogens from attaching. It's an incredibly dynamic immunological shield. Okay, this is where it gets really fascinating. There's a specific protein in this defense system called Z16. Researchers found that this lectin-like protein actually binds to the cell walls of gram-positive bacteria. But here is the genius part of this biological mechanism. Z16 doesn't kill the bacteria. Instead, it aggregates them. It basically clumps them all together into larger masses, trapping them in the outer, looser layers of the mucus. It holds them at a safe distance so they can't penetrate the deep, impenetrable mucus layer near the host tissues. It is basically biological crowd control. It maintains a safe boundary without completely wiping out the local microbial ecosystem. Section 3, the vaginal microbiome. To really grasp why this gatekeeper is so crucial, we got to look at the highly dynamic world of the microbiota living right outside the gates. Here is the lineup. We can clearly contrast our good guys with the high-risk pathogens. A healthy vaginal environment is usually dominated by protective allies like Lactobacillus crispatus. They are awesome because they lower the pH and physically block pathogens. But when dysbiosis hits, high-risk invaders like Gardnerella vaginalis and Mycoplasma hominis completely take over. These guys are bad news. They cause bacterial vaginosis, they release enzymes that literally chew up and weaken that mucus barrier, and they trigger localized inflammation that puts the entire pregnancy in jeopardy. Looking at this risk landscape, you can really see how losing those protective lactobacilli creates an environment primed for a microscopic siege. Without them, the pH spikes, and those high-risk pathogens we just talked about start multiplying like crazy. This is the exact moment when the physical and biochemical strength of the cervical mucus plug is tested to its absolute limits. If the environment gets too hostile, the invaders prepare to strike. Section 4, when the barrier fails. Which leads us to the most critical question of this whole explainer. What actually happens when those fortress defenses crumble? Researchers analyzed cervical mucus from women at low risk versus high risk for preterm birth, and honestly, the differences are stark. Low-risk mucus is opaque, it's paste-like, and it forms a strong, impenetrable gel that stops bacteria in their tracks. But high-risk mucus, It forms a significantly weaker gel. It becomes highly extensible, a physical property known as spin-Burkat, which basically means it's super stretchy. And the real danger here is that this weaker, stretchier structure makes it highly permeable to bacteria. It's essentially like leaving the fortress gates wide open. Let's walk through the devastating cascade that follows this barrier failure step by step. First, dysbiosis allows the pathogens to multiply. Second, because the mucus is weak and permeable, those bacteria ascend right up through the cervical mucus plug. Third, once they are inside that sterile uterus, they trigger a massive intrauterine inflammatory response, releasing all sorts of nasty chemicals. Fourth, those chemicals degrade and weaken the fetal membranes, causing the cervix to ripen prematurely. And finally, step 5, this unstoppable chain reaction triggers uterine contractions and preterm labor. Section 5. Predicting preterm birth. It sounds harrowing, right? But understanding exactly how these biophysical barriers fail is actually paving the way for some incredible medical breakthroughs. Let's look into the future. Scientists are now actively probing mucus permeability to use it as an early biomarker for preterm birth risk. By using fluorescent microbeads and this highly advanced technique called extensional rheology, they can literally measure how easily particles move through a patient's mucus sample. They found out that while negatively charged beads were restricted across the board, the biochemical adhesiveness of the mucus from high-risk patients was severely compromised. Basically, we are learning how to read the mechanical signs of barrier failure before an infection ever has a chance to set in. So, the big takeaway here, it comes back to that word spin-Burkat. Measuring the physical stretchiness and extensibility of the mucus could soon become a standard, life-saving clinical test. Instead of just waiting around for signs of inflammation or early labor, doctors could theoretically test the structural integrity of the mucus gatekeeper super early in a pregnancy. By spotting weak, highly permeable mucus right away, they could stratify risk and intervene long before the bacterial siege even starts. That is a real game changer. Which leaves us with this final, super provocative thought. We've seen today how physical stretchiness, biochemical makeup, and proteins like ZG16 all work together to hold back the microbial siege. But if a simple physical barrier, this incredible mucus gel, holds the key to 15 million lives annually, how soon until we can synthesize or engineer the perfect defense for those at risk? It's a phenomenal intersection of microbiology and reproductive medicine, and it's a frontier that could literally change the world. Keep your eyes on this science, everyone. Thanks for joining us for this explainer.